All right, so again, particle 1 was here, particle 2 was here, particle 1's negative, so the field goes to the right. If we want the field to go to the left so that these two can cancel, then particle 2 has to be positive. That's why they cancel. Alice, does that work for you? Okay, good. Now, do you see then if the green and the yellow true one and oh, that's not correct. This right? E1 and then E2, E2. Good. So you can see based on this cancel out in order for the electric field to be 0. So what I say, I'm just saying E1 is equal to negative E2. And then when we plug everything in, we can see that what will happen is here we will plug in a negative Q. And then this negative sign in front will cancel it and make it a positive. And we see that it's 16 times Q1, which gives us our 48 nanocoulombs answer. Questions? Does that make it, does it more clear now, Alice? Good. Anyone else? No, it's 16 times Q1. It's 13 cubed, obviously, or squared, obviously. Just kidding. No, okay. All right, so we move. Okay, there's the force, the electric force on Q2. What is the only thing that exerts a force on Q2? What is the only thing that could exert a force on Q2? Q1, that's it. So you just use K, Q1, Q2 over R squared. And that's going to be K, Q1 was 3? Okay, and then it's absolute value, right? So it doesn't matter. So that's 3 nanocoulombs times 48 nanocoulombs over, are they separated by 3 or 4? 4, right? By 3. Ah, man, terrible, really terrible. 0.03 meters. 0.3. Oh, it's not 3 centimeters. 0.3 meters. And then you just plug everything in and get your answer, right? So this becomes 144 divided by whatever, 0.09, blah, 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 whatever. So what does that come out to be? What does this answer come out to be? 1.4 times 10 to the negative 5? And that's going to be newtons. Next part, part D. It says determine the x-coordinate of the point at which the electric potential is 0. What is the equation for electrical potential? What symbol do they use on your formula sheet? Delta V, okay. Yeah. Okay. And what's the equation for this? Of course, delta V is equal to K times the sum of Q, like whatever Q I over R. You know, that thing? You know, dot, 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 I is integers, etc. That's not the right formula, I don't think, but whatever. Or is it with I down here and then, no, N down here, and whatever. Okay, but anyways, you get the idea there. So, when we do this, we say, okay, well, what this means, if I get rid of the little, it's going to be, or the electrical potential particle 1 plus the electrical potential particle 2, right? And the electrical potential particle 1 is K, and then it's Q1 over R1 plus K Q2 over R2. Okay? This is not the R1 and R2 from part A and B. Right? Because A and B were both in relation to particle P, remember? The one over there. But this is saying in between them. So if we've got Q1 here and we've got Q2 here, and there's 0.3 meters between them, we're looking for whatever, X marks the spot where the electrical potential is 0. Okay, so I think you can see what we get here. We get K Q1, over R1 is equal to negative K Q2 over R2. And then the thing that helps us be able to do this is we can say R1 plus R2 equals 0.3 meters. That's key right there. Another point. So back to it, the K's cancel, and we can replace, I don't know, which one do you want to replace? Let's replace R2. R2 is going to be 0.3 minus R1. So this becomes Q2 over 0.3 minus R1. And now have an algebra party. So you get Q1 times 0.3 minus R1, which equals, like switching between lowercase and uppercase and all this other stuff. Q2 times R1. So you get 0.3 Q1 minus Q1 R1 equals Q2 R1. And then I can move this over to this side. And so I get R1 is equal to 0.3 Q1 over Q2 plus Q1. And see, so what's nice here is you get Q1 was 3 nanocoulombs? Yeah, negative 3 nanocoulombs. Q2 was 48, so this becomes 0.3 times basically 3 over 45. And 3 over 45 is like what? 1 over 15? So this becomes 0.3 over 15 meters. Does that make sense? Let's put it through the logic test. Is Q1, who's smaller, Q1 or Q2? This is not a difficult question. Okay, you guys are all calculating, that's why. This one's smaller than that one, right? 3 is smaller than 48. So, doesn't it make sense that the point where the electric potential is going to be closer to Q1 instead of Q2? Right? So it's kind of like if you think of, even if, sorry?
Is it 3 over 15 or 3 over 1.5?
It's 0.3 over 15. 0.02. So it's 0.02 meters, right? So hopefully we see that X position is equal to kind of like X1, which was, X1 was at 0.1, is that right? Okay, so X1 plus R1, and that's going to give us 0.12, right? And that's the answer. Thank you very much. Clearly his light is brighter than mine. Said. So yeah, sorry, I did this by memory and clearly. So vision is okay. Is everybody okay? This is negative 0.1 plus 0.02. So then our answer becomes negative 0.08 meters. There you go. Okay. Electric potential. Now we know that that means delta V, right? But what units is that? That's energy per charge, right? If the electric potential is 0, how much energy are you giving? Do you see that if delta V is equal to 0, we're assuming that there is a charge, right? Because they said take a charge and put it there. But that means that energy is 0. And how much energy does it take to bring something? Because remember, if you have this charge, or if I have some charge right here, Q, oh wait, no, it's not the same. Yeah, okay. If I have some charge and I have another charge here, Q2 and it's Q1, if I pull this away, let's say these are both, or this one's a plus and this is a minus, do you see that that's going to do some work? So energy is involved in that. Does that make